Hi, my name is Christoph, and today I'm going to present you our paper Pupil Dilation fulfills the requirements for dynamic difficulty adjustment in gaming on the example of Pong, which I wrote together with my co-authors Michael Barthelmaes, Lisa Altgassen, and Anke Huckauf. When we think of the relation between pupil dilation and task difficulty, in all the papers we usually find the assumption that pupil size will be linearly linked to task difficulty. However, as we know now, of course, tasks can be too difficult, and therefore participants or users will tend to give up, and this will cause pupils to shrink again. So essentially, pupil size is linked to mental effort rather than task difficulty. Well, we thought if we have this relation between pupil size and task difficulty, maybe we can use this information to make interfaces difficulty adaptive and make it optimal for users. When we look into the research on this question, especially for gaming, the link between difficulty and pupil size is assumed to be linear rather than to follow this curved relation. So basically we assumed that pupil shows this curved dilation when gaming or playing a video game, following basically the Yerkes-Dodson law formulated over 100 years ago. And just as pupil dilation, gaming experience, as rated by subjective questionnaires, should follow the same function. In two experiments, we used the gaming classic Pong. Hereby, the left racket is playable by the player, while the computer controls the other racket. And your task as a player is simply to hit the ball and hit it back to the other player's side. We let participants play for 400 seconds, and in between these 400-second intervals, we had questionnaires on the foregoing interval, asking our participants to rate how they experience playing. In experiment 1, the difficulty was manipulated by changing the ball speed, and in experiment 2, the difficulty was manipulated by changing racket size. So for example, for the ball speed, here you can see the ball moving quite slowly, quite boring in the upper left, whereas it is very fast, essentially too fast, at least for me, to properly react in the lower right. Let's have a look into the results. Here you can see the different levels. So with 1 being the easiest level, 4 being the hardest level, and you can see the pupil size set standardized. So this is the average pupil size over the 400 seconds of playing. And as you can see here, it pretty nicely follows what we assumed. So pupil size first dilates, or pupils first dilate when it's getting harder, but when it's getting too hard, people tend to give up and pupil shrinks on average. We also find this to be statistically significant, so a model including this quadratic predictor is always better than the one with the linear predictor only. So here you can see this curved regression together with the confidence intervals. For experiment 2, we had to average level 1 and 2 because they were both very easy to participants, and we ended up with this finding here. It's not so clear as for experiment 1, but still we find this curved relationship and this effect to be significant. So it seems to be that we have this curved relationship for pupil size. Let's look into the results for the questionnaire data. So when we look at the questionnaire data, we see a positive link between the items on pupil size, especially for experiment 1, where effects are significant. So fun, enjoyment, holding attention, focus, and effort put into playing are all positively linked to pupil size. Instead, boredom is negatively linked. This is because this item is inversed. For experiment 2, we don't find these effects significant. However, the descriptive direction of effects is similar. In experiment 2, we also had the 2 control items, whether participants felt good at playing and competent while doing the task, which are also linked to pupil size, in this case, negatively linked. Let's have a look at the results and the pattern of results. So here you can see that the pattern of results, fun, enjoyment, holding attention, focus, and effort, basically follows the inverted U shape that we found for pupil size, with the easiest and the hardest level rated worst. The same pattern is found for experiment 2, and as you can see here for boredom, the pattern is basically inverted. So here we do have a U-shape function, which is due to the way the item is presented or was presented to the participants. Additionally, we have the good and competence rating, which are basically a manipulation check. So we can see here that the levels were rated differentially difficult. So let me conclude. Pupil dilation indeed reflects under and overload during gaming. So we can identify fit, we can identify when people are bored playing, but we can also identify when people are overloaded and therefore make adjustments to difficulty. We think that difficulty of games or interfaces could thus be adjusted using pupilometric information. However, there is need for further research, so in next steps we would like to test the more applied scenarios. This could be case-based interaction, this could be outside the lab and of course using a less restricted game. We can make use of more advanced signal processing methods. For example, we could look at oscillations in pupil size, which are also informative about the mental effort a player or a user puts into operating a system. And we can test for different types of interfaces. This could be a case-based interface, or it could be an adaptive learning software. For the context of co-game, for example, it could be interesting to use pupil size as information on the mental effort that a player or user puts into operating a system for adjusting dwell times adaptively. So thanks a lot for listening. Have a look at our paper.